Good evening, everyone. A warm welcome to Dr. Mahesh Naik, sir, for our IIT Jam lecture series. You can continue, sir. Over to you.
Yes, thank you. So let's begin with things that we did yesterday. So we saw in the later part of the lecture the definition of eigenvalue, eigenvector, followed by some properties of eigenvalues and eigenvectors. So I've put those properties specifically for some matrices, what kind of eigenvalues we expect or will have. So in case if the matrix is real symmetric and Hermitian, then the eigenvalues will be real. Likewise, in case of skew symmetric, will be either zero or purely imaginary. In case of triangular matrices, it will be the principal diagonal elements. Likewise, for real orthogonal, it will be possibly, in case of real, it will be plus or minus 1, or otherwise e power iota theta, and similarly the negative. For idempotent, it would be 0 or 1, nilpotent 0, involutory will be plus or minus 1. Okay, so keeping this in mind and uh, going through the theoretical part as well, let's look at some examples which will involve the information about rank, the system of linear equations, okay, and then the eigenvalues and eigenvectors. So just to proceed with, um, let's take this example, which is the number of solutions of the system y equal to 3x plus 3 and y equals 5x, sorry, 3x plus 5. Okay. And the possible options are 0, 1, 2, or infinite. The number of solutions. These are the options. So we have seen rank yesterday, and we have seen the possibility of solutions in case of system of linear equations, both homogeneous as well as non-homogeneous. So utilizing the information of that, yes, how do we go about this?
So we'll convert into matrices,
Mhm.
uh, then we will reduce into echelon form, and then we'll solve the system of linear equation.
Correct. So we can write this as minus 3x plus y equal to 3 and minus 3x plus y equal to 5. Yes, we can bring it down to the matrix form. We can find the rank and do all of it. Okay, but otherwise, just by looking at this, also can we check if it is consistent or inconsistent?
Inconsistent.
Yes, I will have infinitely many sections.
Yes. So having the values of x and y, which give both the values 3 and 5, will not be possible. So that's inconsistent, and so we can go with the option 0. So the number of solutions of the system would be 0.
So, so both line is parallel line now.
Yes. So they will not meet. Okay. Is that clear?
Yes, sir.
Yeah. So let's proceed with next. The number of linearly independent eigenvectors eigenvectors of the matrix 5, 1, -1, 3. Okay, so we want to find the number of linearly independent eigenvectors in this case. Okay, and the options are 0, 1, 2, or 3. How should we proceed? One way is we can find out the eigenvalues and then accordingly we can proceed, or otherwise we can find the rank and the number of, the order minus rank will also help us in finding the number of eigenvectors. Okay, so let's find the eigenvalues in this case, which would be 5 minus lambda, 3 minus lambda, -1, and +1. Okay, which would give us 5 minus lambda into 3 minus lambda +1 equal to 0. Okay, so what are the factors in this case? 15 minus 5 lambda minus 3 lambda plus lambda square plus 1 equal to 0, which is lambda square minus 8 lambda plus 16 equal to 0. So that's lambda minus 4 the whole square. And so lambda equals 4. Okay, so we can find the eigenvector for lambda equal to 4, which would be found by writing ax equal to lambda x, and we want to find the value of x, which will be of order 2 cross 1. Okay, and so we can say a minus lambda I into x is equal to 0, which gives us 1 minus 1, 1 minus 1. Okay, into x, which is x1, x2 equals 0. So that produces only one equation, which is x1 minus x2 equal to 0. And so x1 equals x2. So the eigenvector x is x1 and x1. So x1 times 1, which is just 1, 1. So how many eigenvectors we have in this case?
Unique.
Just 1. Okay, so the algebraic multiplicity of lambda equal to 4 is 2, but the geometric multiplicity is equal to 1. Okay. Also, further, we can connect this with the concept of diagonalization, where a matrix is diagonalizable if the algebraic multiplicity is equal to geometric multiplicity for all the eigenvalues. Okay, so this is also an example of a matrix which is not diagonalizable. Okay, let's proceed with some more examples like this. Okay, so if we have a matrix B, which is given by 3, 1, -2, and 0, and we want to find the value of B cube. Okay, and the options for B are 7B plus 6I, 5B plus 4I, 3B plus 2I, and 9B plus 8I. Okay, so these are the options for the matrix B cube. So should we proceed? Whenever it comes to finding the higher power, we will. So we'll find the characteristic equation of B first. Okay, so that will be given by lambda square minus the trace of B, which is 3 lambda, plus the determinant of this, which is given by 0 minus -2, which is +2. Right? Now we can apply Cayley-Hamilton theorem, which says that every characteristic equation satisfies its own matrix. I mean, the matrix satisfies its own characteristic polynomial. So we have b square minus 3b plus 2i equal to 0, which gives me b square is equal to 3b minus 2i. So we have got the value of b square and we want to find the value of b cube. So b cube can be written as b square into b, and then the simple calculation 3b minus 2i is the value of b square, which gives us 3b square minus 2b, but b square is 3b minus 2i and minus 2b, which is finally 7b minus 6i
plus 6i.
plus 6i. So minus plus, this was 0 and this was plus. Is it plus or minus?
Minus 6i.
Minus 6, and I think
Mm.
the options are wrong. Should be 7b minus 6i. Okay, so that's an application of Cayley-Hamilton theorem, which tells us when it comes to higher powers, we can always use the characteristic polynomial, and we can apply Cayley-Hamilton theorem, which will help us in bringing it down to the required expression. Okay, let's go to another example. Okay, so which of the following cannot be eigenvalues of real 3x3 matrices? So we have 4i, 0, 4i. Then it's 2, 2, 3 e power eta theta, comma e power minus eta theta, comma 0. Okay, and 3i, 1, 0. Okay, so you want to check which of the following cannot be the eigenvalues of a real 3x3 matrix. So we know that the matrix is a real matrix. Okay, and you're looking for the possible eigenvalues, and out of this options, which one is not a proper choice?
Option A and I think option D.
Option A and option
D.
ACD.
This is minus 4i. The first one is 4i, 0 and minus 4i. Okay, so what is the reason to claim that
Because here the matrix entry are coming from real and their characteristic polynomial. In their characteristic polynomial, the coefficient must be real. And here we see the root of it characteristic polynomial. If in complex, then it should be the conjugate pair because for getting the real coefficient of the equation, it must be occurring conjugate pair. Otherwise, it would not work.
yes. So as you said, the coefficient should be real. Moreover, the trace of the matrix should also be real,
Yes.
right? And the determinant also should be real. So let's use this information because we know that the eigenvalues are connected to the trace and to the determinant. because trace will be sum of the eigenvalues, which is lambda 1 plus lambda 2 plus lambda 3, and the determinant would be lambda 1 into lambda 2 into lambda 3. So let us check which of these pairs will give us real trace and real determinant. So the first case, sum would be 0 and the product will be 0. So that's a real value for trace and determinant. So this is eligible to be the eigenvalues. 2 to 3 when added will give a real value, product will be a real value. Okay. E power iota theta is nothing but the Euler's expression. So we have E power iota theta equal to cos theta plus I sin theta, and E power minus iota theta is cos theta minus I sin theta. So addition would be 0 with 0 as well, and the product will be equal to 1. So again, the sum and the product is real. And in this case, if we add this, the trace will be equal to 3i plus 1, which is imaginary, which doesn't fit into a requirement. So yes, option D is the set of eigenvalues which are not eligible for a real matrix. Okay.
Okay, sir.
Let's take another example, again based on eigenvalues and some additional thoughts. If A is a matrix satisfying A square equal to I and a trace of A equal to 0. Okay, so here in this case, this I is an identity matrix of order n cross n. Okay, and the question is, the options are then the determinant of A must be 0, B, determinant of A must be plus 1, third option is it must be odd dimensional. I mean, the matrix must be odd dimensional, or it must be even dimensional.
So third and fourth are wrong,
Okay, why is it so?
sir, because it's a involuntary matrix, and so A square is where A is equal to its inverse, and so an is identity when n is even, and we get a when is n is odd. But in third fourth, it is said it is must odd dimensional or even dimensional.
Right.
So it may be, but it doesn't mean that it always satisfy even or odd.
Right. So let's look at this in a different perspective. See, what we know is A square is equal to I. Okay, so by using Cayley-Hamilton, we can go back to the characteristic. We can go back to the characteristic equation, which is lambda square minus 1 equal to 0 is satisfied by this. Not characteristic, but a kind of annihilating polynomial. Okay. Now, what we see is if the order of characteristic equation of the matrix is less than the order of the matrix, okay, then some of the eigenvalues will be degenerate, right? So which means some of the values will be repeated. And with the help of lambda square minus 1 equal to 0, the possible values of lambda would be plus or minus 1. Okay, and since, as I said, we have lambda square minus 1 as one of the polynomials satisfying with respect to A, which is of order n cross n. A has to be a matrix of order n cross n because I is of order n cross n, right? So, and because of lambda square minus 1 being equal to 0, where 2 could be lesser than n, okay, there will be degeneracy in the sense the values will be repeated. So in case if this plus and minus 1 is repeated, let's assume these are the values which are repeated, okay, and only plus 1 is repeating or only minus 1 is repeating, what will happen to the trace of A? So if we take plus 1 and minus 1 as repeating, like only plus 1 is repeating, okay, then in that case, the order of matrix could be 3 because there'll be 3 eigenvalues. If we take minus 1, again it will be 3, but the trace will not be equal to 0. So trace will only be equal to 0 if this kind of pairs are occurring in even numbers, right? And this will happen only if the matrix is of even dimension. Is that making sense? So I'll repeat this
Yes.
a square minus, okay. So there is a possibility where plus 1 is repeating. So if plus 1 is repeating, it could be plus 1 minus 1. Or otherwise it can be minus 1 comma minus 1 comma plus 1. But in either case, we won't be able to get trace equal to 0. So that means we want these numbers to repeat in both the numbers to repeat. So it should be even.
Yes. Yes, sir, got it.
Yes. Okay. Let's take an example, which is
Sir, can I ask a question?
yes, yes.
Yes, sir. In the previous class, have you put those inequalities or something useful result to determine rank or anything comment about rank?
Yes.
Like, yes, have you written the previous class in the previous class? Because I could not join due to my illness, so I missed the session.
Okay, this entire notebook is there
Okay,
with me. So I'll
okay,
share it with the
okay,
organizers. They can send it to you.
okay, okay, sir.
Right now, today I'm writing in a new notebook.
Okay,
Yesterday's notebook is in my other system.
okay, okay, sir.
Maybe
No
tomorrow I'll
problem,
share both.
no problem.
Okay, yeah. So let's take this example related to eigenvalues. Eigenvalues of a matrix. So suppose we have a matrix A of order 3 cross 3, and determinant of the matrix is 4, and the trace of the matrix is equal to 6. Okay, and uh, the first two eigenvalues are lambda 1, lambda 2, which are 1 and 2 respectively. Okay, now the question is to find the determinant of a square minus 3a. So we have determinant of a as 4, the trace of a as 6, lambda 1 and lambda 2 is given, that's 1 and 2. And we want to find determinant of a square minus 3a.
Hello, sir. Here, lambda 1, lambda 2, the eigenvalue, and 1 and 2 respectively. What is it? Hello.
Yes, yes, tell me.
Yes, lambda 1, lambda 2, and 1 and 2. What it is?
Yeah,
1 and 2.
lambda 1 is 1 and lambda 2
Sir,
is
okay.
yeah.
And it is 2 cross 2 matrix. Okay, sorry, 3 cross 3. Okay, okay. And
Yes,
there from I think another eigenvalue is coming out from 6 minus 1 plus 2.
yeah, you can find that way.
Hmm.
So what is the third eigenvalue? 2.
It is 6, 3, 3. Trace is
Yes,
equal to 6 and 1 plus 2, 3, 3. Minus 3. Minus 3, no, plus 3. Trace is equal to sum of the eigenvalue.
Yes, yes. Also, the product is equal to the determinant.
It is 4. Okay.
It's not matching, na?
Yes, yes.
Yes, yes. Let's take the determinant also equal to 6. So in that case, lambda 2, I mean the lambda third value of lambda will match, and so we'll have lambda 3 equal to 6.
Yes, sir.
3, sorry. Okay, so we have all the 3 eigenvalues. Now, these are eigenvalues of A.
Yeah,
Right? So
and similarly, you can get eigenvalue of A square just by raised to the power eigenvalue of the A by its
correct.
index.
Yes, so the eigenvalues of A square would be 1, 4, and 9.
Yeah.
And for
And
minus
minus 3
will be just
minus
back
3. Yeah.
minus 3. So
Minus
that's
2.
minus 3, this is minus 6, and this is minus 9, right?
Yes. Minus
So
2.
minus 2, and 0.
Yeah.
Okay, now we wanted to find determinant of A square minus 3A.
It's
So we know
equal to
that
0.
determinant, yes, so determinant of this matrix will be simply the product of its eigenvalues. So let's say lambda 1 dash, lambda 2 dash, and lambda 3 dash, which is in this case minus 2 into minus 2 into minus into 0, which is 0.
Mm.
Okay, let's take a question on eigenvectors.
Sir, the number in the fourth column, what are they?
Fourth column, it's minus 2, and 0.
Where does it come from, sir?
This A square minus 3, you're saying?
No, sir. The last column, minus 2 lambda 1, minus 2
So
lambda.
minus 2 is the eigenvalue of A square minus 3A, which I'm denoting with lambda 1 dash. Clear?
Okay, sir.
Likewise, the eigenvalues of A square minus 3A, which are this 3, I'm denoting that with lambda 1 dash, lambda 2 dash, and lambda 3 dash. So that here I can
Uh,
multiply lambda 1 dash, lambda 3 dash.
because because eigenvalues are undergoes linear transfer linear change of scale remain intact, change of scale and addition or subtraction by some constant multiple, they
Right.
will change accordingly.
So if the eigenvalue of A is lambda, and eigenvalue of A raised to n will be lambda raised to n. Of Ka will be K into lambda.
Yes, yes,
Also, for A inverse, it will be 1 by lambda if the matrix is non-singular.
yes.
Okay, let's take one example on eigenvectors and then we'll change the track. So in case if we have the matrix as 1, minus 1, 2, 0, 1, and 0, 1, 2, and 1, Okay, and one of the eigenvalue is 1. So one of the eigenvalue of this matrix is 1, and then the eigenvectors corresponding to the eigenvalue 1 are. So the eigenvectors corresponding to eigenvalue 1 are, so we have some options. Alpha times 4 to 1, 4 to 1, such that alpha is not equal to 0 and alpha is real value, or alpha times minus 4 comma 2 comma 1, again alpha not equal to 0. Okay, because if alpha is equal to 0, the vector would turn out to be a 0 vector, and we know that eigenvector can never be 0. Alpha root 2 comma 0 comma 1, alpha not equal to 0. And lastly, the fourth option is alpha minus root 2 comma 0 comma 1. Again, alpha not equal to 0 and it's a real value. Okay, so okay, so what we need to do in this case is simply we'll have to proceed with the row echelon form.
Sir, 1 second trying and on just for 1 minute.
Yeah. Yes, so what is the outcome of this? You know that the eigenvalue is 1. So AV equal to V. Okay. And we have the matrix itself. We can go for A minus lambda, A minus I times V equal to 0, which would give us 0, 0, 0 in the diagonal.
Sir,
Minus 1.
option 1, option A, alpha into 4, a comma 2, 1, alpha not equal to 0.
Correct. Okay, so what is the first equation? That's minus x2 plus 2x3 equal to 0. Second one is entirely a 0 row. And the last one is x1 plus 2x2 equal to 0. So that gives us x1 equal to minus 2x2, x2 equal to 2x3. Right?
Yes.
Is my operation correct? So x1 is minus
Yes,
2.
yes. And here x2 is the free variable because corresponding row is 0, 0, 0. So taking x2 as something alpha, and according to we will find x1 and x3.
Yes. So minus 2, 1, 1 by 2, which is equivalent to saying minus 4, 2, 1. Is that negative sign coming into picture? Yes, no, it is there, no? Minus 4, comma 2, minus 4, 2, 1.
Yes, yes. So I am taking extra minus. That is why it got plus.
Okay.
Yes, yes.
So minus 4, 2, 1 is the eigenvector, and any multiple of this will be an eigenvector of the eigenvalue 1.
Okay.
Okay. Let's take one example based on higher power of a matrix, and then we'll go to the application part of the topics that we have covered. Okay, all these are questions have been taken from some of the other sources connected to the exam. Okay, so if the eigenvalues of a 3 cross 3 matrix are, so A is a 3 cross 3 matrix and the eigenvalues are 0, 1 and 3. And the corresponding eigenvectors are also given. So that's 1, 1, 1 followed by 1, 0, minus 1 and 1, minus 2, 1. Okay, and the question is, then the matrix A power 4 is. So we have 4 options for this: 41, 81, 40, minus 81, 0, minus 81, and 40, minus 81, 41. So this is one possibility. Minus 82, 81, 79, minus 81, minus 81, plus 81, minus 81, 75, minus 81, and 83. The third option is 14, minus 27, 13, minus 27, 54, minus 27, and 13, minus 27, 14. Okay, so we are looking for the matrix A power 4, and the information that we have is the eigenvalues are this. Okay, so any idea how should we proceed?
Sir, option A.
Option A, why?
Because 0 and 1 and 3 is the eigenvalue of A. Then we can power 4, then that is the eigenvalue of A4.
So that will be 0, 1, and 81, right? Okay.
And then
So
the product
since
is
we know the
the
Hmm. Product is the
Yes, sir. Continue.
determinant. Hmm. So trace of this a raised to 4 will be 82, right? And the determinant of a raised to 4 will be the product of all three, which will be 0. So we have some information about a raised to 4, like we know the trace of this, and we know the determinant of this. But getting the determinant of all these matrices, which with this huge numbers, will be a difficult task. But we can check for the trace of a raised to 4. So these are the three options for a raised to 4. So if we look at the trace of the first one, that is 82, right? So that is matching with the trace of a raised to 4. For the second matrix, what is the trace?
82.
82. And for the third one is again 82, which means this information is not helping us in finding the value of a raised to 4, because the trace is equal for all three and it is matching with the trace of a raised to 4. But this type of logic can help you in ruling out the matrices, the options. Okay. Let's look at the next part, that is, since 0 is the eigenvalue of 0 is one of the eigenvalue of a raised to 4, and we know that the eigenvector will still remain the same. So 111 is the eigenvector corresponding to eigenvalue 0. These are the corresponding eigenvectors, okay, for 0, 1, and 3 respectively. So what we know is, we know that for any matrix, when we multiply the vector, we have that equal to lambda times the vector. So in this case, if I talk about a raised to 4, a raised to 4 into vector will be equal to lambda times the corresponding vector. So if I take specifically the eigenvalue 0, okay, so 0 into v will be equal to 0. And on the left hand side, it will be a raised to 4 into v. But the eigenvector for this particular eigenvalue is known, that is 1, 1, 1, right? So we have this relationship where if the matrix a raised to 4 is multiplied with the vector 1, 1, 1, it should produce 0, 0, and 0. Okay, so let's use this information. Let us multiply this matrix with 1, 1, 1, the eigenvector 1, 1, 1. So it is simply this row getting multiplied with the column. And since all of them are 1, we just have to add them, like 41 plus 81 plus 40. So is this giving us equal to a null vector, 0 vector? The first value after multiplication itself is non-zero, even the second. So this is not a raised to 4 for sure, right? Next one would give you, after if you multiply this with 1, 1, 1, the first element will be 0.
Third one will be true.
No, right?
Third one.
Right. Third one. So if we add this, it is 0, this is 0, and this is 0. So a raised to 4 would be this matrix. Okay, so the information about eigenvalues and vectors were known, but that helped us with the trace. That was not enough to get the value of a raised to 4, but we could have deleted some options if there would have been many options, not satisfying a power 4 equal to, the trace equal to 82. Okay. Okay, so eigenvalues can be further considered into the diagonalization part of the matrices. We can check if two matrices are similar or not by using diagonalization. Okay, so now let's proceed to some applications of the areas that we've seen. Okay, so majorly what we have seen is we have seen eigenvalues and eigenvectors. Rest of it was all the supporting stuff. Could be rank, could be system of linear equations, and all of that. Okay, so this is especially when it comes to the area of data science, where a lot of data is handled. Accordingly, we have to do operations on a huge amount of data. And doing this operations on individual records would be very difficult. So putting the data into a matrix form will surely help us in doing the operations quickly. At the same time, the expressions, the program can be brought down to a simpler um, format, so the optimization will be possible. Likewise, many other things will become simple when it comes to putting the data in terms of the matrix. Okay. So before we proceed there, so one of the application of matrices would be having the data sets represented as matrices. And when we talk about rows and columns, so with respect to data set would be something which has information in terms of features or variables. So let's say variable one, variable two, variable three, and so on. Okay, so there'll be some features, there'll be some which are, I mean, these are some variables which are termed as features in case of data science, and we'll have record of all these features for different individuals, different objects, could be people, and so on. So likewise, we can have record of all of this, and this will go as a matrix. Okay. Now, if you look at this data has to be visualized, or this data has to be understood with n dimensions, which will be a very difficult job even when it comes to operations. So there is a technique in statistics called as PCA, which stands for Principal Component Analysis. Okay, where what we do is for the data that is available, we find something called as covariance matrix. Okay, so we calculate something called as covariance matrix. So covariance is a measure of variance between two variables. Okay, so this matrix will always be a symmetric matrix because this matrix will have the variance of x1 with x1, x1 with x2, x1 with x3, and so on. And likewise, x2 with x1, x3 with x1, and so on. So covariance is nothing but it is showing how a variable is varying with respect to another variable. In other terms, we use proportion, direct proportion, inverse proportion to explain that. But in statistics, very specifically, we calculate covariance matrix. Okay, so it gives the exact value of how much the value is varying with respect to another variable. Now, once we have this covariance matrix, we can find eigenvalues of this matrix. Okay, and once we find the eigenvalue, so in case if I'm dealing with a with a data set which has three features only, then the covariance matrix will be of order 3 cross 3. Then I will have three eigenvalues, lambda 1, lambda 2, lambda 3. And possibly if everything goes proper, we will have three eigenvectors, v1, v2, and v3. Okay. Now, these three eigenvectors are accordingly the three vectors in plane. Okay, and these vectors accordingly represent the information of the data set. So it might happen that the total variation that we have into the data set is maximally explained by lambda 1 and lambda 2, and lambda 3 is hardly explaining any part of it. So in this way, what we can do is we can just get rid of one of the dimension of the data. So the data which had 3 cross 3 dimension can now be brought to 2 cross 2. So what we have done is we have reduced the dimension, and we know that when it comes to computations, how easy things become when the dimension gets reduced. Okay, so this is principal component analysis, which is also used in image compression, because we know that if we work with uh, grayscale images, okay, these are images which are nothing but matrices. Okay, so if the image is of 28 cross 28 pixels, which means there are 28 rows and 28 columns, those many pixels. So each pixel will have a value between 0 and 255. Okay, where this number between 0 and 255 is the intensity of that particular pixel being bright or dull. Okay, and so this matrix which I'm talking about of order 28 cross 28 if I calculate the covariance matrix, again, that will be of order 28 cross 20. And if I run PCA on this, out of those 28 dimensions that we have, we can find out which eigenvalues have the maximum magnitude, which explains like how many eigenvalues explain most of the data that is there. So in case there is a possibility that from 28 rows into 28 columns, where we will have 28 eigenvalues, we might come down to something like only five eigenvalues. So let's say lambda 1, lambda 2 up to lambda 5. Okay, so that is a huge reduction in the data that was originally there into the image. Okay, and that is helping in reducing the size of that image, but at the same time not removing a lot of information. So we are not compromising on the information, but at the same time we are preserving the data. Okay, so this is one place where matrices, eigenvalues, eigenvectors are accordingly highly useful. One can think about why we always represent the data on XY axis only, and why these axes are always perpendicular to each other, and why the direction of X is this or Y is this, and so on. Can't we have any other axis where the data could be represented more efficiently, and so on? Okay, so the answer would lie into this kind of technique, which is PCA, and this new axis would be nothing but the eigenvectors actually. Okay, so image compression is one area. Similarly, if the data is stored in matrix form of any other object, even that can be compressed. So we can have gene expression data, facial recognition. So all these things would go into the application. Secondly, in case if we have the matrix of distance, okay, so like again, let us go for some variables x1, x2, x3 up to x5, and maybe we have x1, x2, x3 up to x5. And this matrix is suppose denoting the distance between x1 and x1, which will be 0. Distance between x1 and x2. Likewise, if we have this matrix, which is a distance matrix, then this distance matrix can be used for clustering. So with clustering, I mean, if we have large amount of data, we can accordingly find the distance between every object, okay, and the points which come closer can be put in under one cluster, and the points which come close, which are far away from each other, and then the ones which are close will be put into another cluster, cluster 1, cluster 2, and so on. So when I'm talking about the distance right now, it is not distance between the numbers. It could be any two records. So maybe the data of some kind of customer experience, or maybe HR related data, marketing data. So if we have data which is in some form, by using Euclidean distance or any other like Minkowski's distance and so on, the distance can be calculated, and based on the distance, the suitable distance, we can accordingly check whether the points are close or far away from each other, and then we can make up some clusters. So this is also called as unsupervised learning, where we try to find out how these points are close to each other, and the data that we have uh, accordingly gives us some kind of information about why these points are close to each other. Is there some other property, some other characteristics, and so on. So again, the operations happen on matrices. So matrix will be useful in such case. Moving ahead, everybody is aware of the boom of AI and machine learning and deep learning. Okay. So basically, what we have is we have models which learn from the data, and once the model learns from the data, accordingly they start working on unknown data. So ideally, what we have is we have a data set consisting of some number of records. Okay, so from this data set, the model will learn. So model will absorb enough of information from the data set. Okay, and then Once the model is assessed and is found to be a good model based on various metrics, based on various predictions, then we can accordingly send some unknown data to the model for prediction purpose. Okay, that's how the models will be used. Now, these models, which are being continuously evaluated on the data sets, so we have an option, we have a type of model called as deep learning model, where we use the weights on the data, and then we have some biases added to it. Okay, so in this case, when this weights and this input values are being used, this is nothing but the operation of matrix multiplication. Okay, so these weights are being continuously updated so that we reach the best possible accuracy. So deep learning is completely linear algebra, and then to check if the model is giving good outputs or not. If it is not giving good outputs with respect to the actual values, then what we do is we accordingly update the weights, and this updation happens with something called as gradient descent algorithm, which is entirely calculus. Okay, so what we do is, if this is something called as the graph of the loss function. So with loss, I mean the value predicted by the model and the actual value. Okay, by using that, we can define different loss functions, and we can try to find out the weight in the model or the parameters of the model which give us the minimum loss. Okay, so in a way, we find the minima, and till the time we don't reach this minima, we keep on updating the weights, we keep on updating the parameters. Parameters are the instances of the model which can keep on changing till the time the model reaches the maximum accuracy. Okay, so all these learning models have this basic concept, and then accordingly there are additional customizations which can make them different from each other. Okay, then we have convolution operations, where matrices are used. So in case if I am trying to make a model for image recognition, okay, so suppose I'm feeding the model different images of different sizes. Okay, different images. The sides could be eventually brought down to the same structure. Okay, and I'm all these images that we have. Let's say they have a label that the image is of dog or of a cat or of a cat, dog, and so. Let's go for only two images right now. So the model, this image will be actually a matrix. Okay, and what we can do is we can convolute this matrix with a smaller matrix, okay, which actually multiplies with this entire matrix in this particular fashion, okay, with every part of it. So let's say this is something like uh, 250 cross 250 matrix, and there is a convolute matrix or a filter matrix which is of order 3 cross 3. So this part of this matrix can be multiplied with 3 cross 3. So when we multiply this kind of matrices, this is kind of filter which.
Hello.
Wait. Yes, sir. Are you there?
Hello. Am I
Yeah.
audible?
Yeah. Sir, you're not audible.
Hello. Now,
Yeah, fine.
am I audible now? Yeah.
Yeah.
So I was talking about this filter matrix, which is going through all this, I mean, the entire image one by one, and likewise, it gets the information of all of these corners of this image. Okay, and likewise, if we have more filters, these filters which are in the form of matrices could be some special matrices, like we have matrices for rotation, reflection, translation, and so on. So likewise, we can have some proper filters uh, created for image recognition, which will extract the information and will get the information. So likewise, what happens is the model will accordingly extract the data from the image with the help of this matrices, will accordingly understand what is the pattern in the image, and eventually when an unknown image is given to the model, those patterns will be recognized as I mean the animal's dog or cat. Okay, so here in this case, we do this convolution operation, which is similar to convolution operations that we have into Fourier series, Laplace transformation and so on, or fast Fourier transform, or any other transform, in fact. Okay, then in case if we have multiple variables, let's say x1, x2, x3, and so on, and let's say there are only three variables and we have a variable y, and this variables uh, can help in finding, or these are variables which accordingly help in predicting y. So y could be called as a dependent variable, x1, x2, x3 can be called as independent variables, and we can try to set up an equation of the form y equal to m1 x1 plus m2 x2 plus m3 x3 plus some intercept, okay, which we know that is a equation of a line of a plane and so on. Okay. Now, if y and x1 and x2 and x3 have linear relationship, only then we can accordingly generate such an equation from the available data of this particular type. Okay, this is called linear regression, where we are trying to regress y with the help of predictors x1, x2, x3, and so on. Okay, and for an example, if y is my test score, I know that my test score would be ideally dependent on how much time I study, how much is my IQ, could be some other variables which can be understood by doing some research, okay, by reading some literature, and by taking proper variables into consideration, we can find out the value of y for unknown values. So if somebody is studying for some 10 hours of time a day with some IQ and with some other variable, we can try to predict the value of y. So this is called linear regression, where again the data would be a large data set. Okay, and all these values of x1, x2, x3, and y will accordingly help us in calculating these coefficients that we've written here, m1, m2, m3, and this intercept and so on. So in this case, the data could be put into a proper form, into the matrix form, and then to calculate these coefficients, we can use this particular formula, which you all can see. It is nothing but matrix multiplication, the transpose, the inverse, and so on. So this will give us all these coefficients actually. That's m1, m2, m3, and so on, and c as well. So there is something called as classical linear regression model, which utilizes this normal equation and finds the value. So again, matrix uh, is being used to calculate or develop the model. Okay, by default, all the transformation operations which come from linear transformations, like rotation, scaling, translation, and so on, are by default being used in computer vision, computer graphics. Okay, and also when we convert some three-dimensional scenes to two-dimensional and so on, then we make use of the projection matrices. Okay, so these are some areas where matrices are being used. So one can actually look at the type of the matrix and can get more deeper into what type of data is of what type of matrix and what kind of things can be known in the very beginning, because when it comes to making a model, most of the times the things are R&D. So if we can have some kind of initial analysis where we can have the data set, which is eventually converted to a matrix, and by the known properties of matrices that we have into our theory, if we can conclude whether the model will be possible or not. For example, in this case, if we look at this formula X transpose X inverse, so if X transpose into X is coming out to be a matrix where the determinant is 0, okay, then there is no possibility of getting this coefficients because the inverse will not exist. So likewise, some built up on the real world data and the theory that is already being worked out. So that's how we can make things more efficient when it comes to application. Okay.
Yes, sir. Trying to connect something new in the field of application. People, I am not ever seen this application of a principal component analysis. I have heard of this term only, and but
Okay. Mhm.
okay, this is quite interesting
Yes.
and
All
topic
of
for
linear
further
algebra.
exploration.
Correct, correct. All
Yes,
of linear algebra, matrices, and calculus is deep into the applications of things that are happening around us right now. I mean, the entire AI is LLMs, NLPs, all of this they use this, but of course, there is a um, touch of statistics, probability, which make it more applicable. So solely maths will help with the computational powers and everything. But when it comes to interpretation, when it comes to the uncertainty, especially, their probability is what will make things better.
yes, sir.
Probability and probability distributions. Yes.
Yes.
So, on the behalf of the Department of Mathematics and Wilson College, I would like to extend my heartfelt gratitude to Dr. Mahesh Sir for conducting an excellent 4-day online lecture series as a part of IIT Jam lecture series. Your session was insightful, well structured, and highly informative. The clarity with which you can explain each concept has greatly strengthened our participant understanding and prepared them well for their examination. Your dedication, time, and sincere effort have made a significant academic impact on our learners. We will be sharing the feedback form by tomorrow, and I request all the participants to fill the feedback form because your feedback is highly important for us for conducting more session in the future academic year. So thank you once again, sir, for supporting our department and being a inspiring resource person. Thank you so
Thank you
much.
so much. Thank you for the invitation. Yes. Can I leave?
Yeah, sir.
Thank you so much. Bye, everybody. Good day and all the best.
Thank you,
Yes.
sir.